Hello student, good morning to everyone. I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the orientation and the reactivity of the substituent group. There we have seen some of the monosubstituted aromatic compound producing the orientation like as ortho, meta and para. In some of the cases, ortho and para are predominant, whereas in some of the cases we found that meta is predominating. Why this is so? The answer of this question we already discussed. If you know the resonating structure of this particular, automatically the answer will come. So more precisely we are going to learn today. Look at what we are going to discuss today. See, the theory of orientation effect means A part, effect of electron donating group. As I already told you that the monosubstituted benzene or the benzene either containing electron donating group or it can containing electron withdrawing group. So two possibilities are there, and therefore we are going to learn effect of electron donating group. If electron donating groups are present, what type of the orientation they show, that we are going to learn today. Suppose let us consider here the formation of sigma complex formed by attack of electrophile at the ortho, meta and para position of toluene. What we are considering today, we are treating the toluene with the electrophile, and as we know that orientation means the attack of nucleophile can occur at ortho position, meta position and para position. Let us see. As we know that effect of electron donating group, and as we know that alkyl group are electron donating group, and therefore here I am drawing the structure of this compound. Everybody knows that this is a structure of toluene, right? This is a structure of toluene, and this is a monosubstituted benzene, you can remember, and the group, the alkyl group attached to this benzene ring, and this group is nothing but as an electron donating group, means it releases the electron to the benzene ring, and that's why the reactivity of that benzene is greater as compared to the normal benzene. Normal benzene, we know that it is a nucleophilic in nature, and this benzene readily undergoes electrophilic reaction, electrophilic substitution reaction, and therefore now when the benzene is a substituted, specifically here alkyl group, it is a electron donating group, it giving the electron density to this benzene ring, and then as we know that this toluene is a aromatic compound, and as we know that the tendency of that aromatic compound, they readily undergoes electrophilic substitution reaction. Let us see here, when we are adding, representing here E plus means electrophile, and when this electrophile attach, there are three possibilities are there. This is the toluene or this alkyl group. Look at these two position adjacent with respect to that methyl group. They are ortho position. They both are identical. Then look at these two position. These two position are also identical, and they are known as meta position. And look at exactly opposite to this methyl group, so that is a para position. So there are three orientations are there. One is ortho, meta and para. Orientation you are going to get here ortho, meta and para, right? Ortho, meta and para. Electrophile is going to attack at ortho, meta and the para. So because here we are trying to find out the effect of this group, means the electron withdrawing group. What is happening, that we are going to discuss over here. And now look at here, this double bond attacking like this on a electrophile attached to that benzene ring. What is going to happen here? Look at the structure carefully. What do you see over here? Rest of the thing you write down as it is. Methyl group, this double bond and this double bond, they are as it is. When this double bond shifted, this double bond attacking on that electrophile, the bond is formed between the electrophile and this carbon atom. When this double bond forming the bond with that electrophile, the leaving behind the positive charge. When this double bond shifted like this, ultimately this carbon atom showing electron diffusion in nature, means there are here positive charge, and this positive charge we know that it is a carbocation, right? And this carbocation, as we know that by the residue, and after formation of that carbocation, whether it is a stabilized or destabilized, there are a number of factors which can stabilize or which can destabilize the residue, this effect and this carbocation. And now look at here, and this double-headed arrow indicate the resonating structure. And what is resonating structure? What are the condition for the resonance or the rule for the resonance? You already learned in your previous classes. Now look at carefully. Now this double bond shifted from here to here, neutralizing this positive charge, and you are going to get the product like this. When the other thing, this CH3 and this double bond remains as it is, the hydrogen atom and the electrophile is shown here, they are as it is. When this double bond shifted from here to here, the double bond must be there. Now at this corner point, what do you think? What kind of the charge present on this carbon? At this corner point, there will be a positive charge, right? Now next one, you can draw the structure. Now this double bond now shifted from here to here, forming as a double bond here, and you are going to get the product. You are going to get the next structure, double bond here. Now it is a methyl group. Now here is a positive charge, and this double bond remains as it is. One of the hydrogen atom still there, and electrophile as it is. If you observe this structure carefully, what do you see here? This is, I am numbering these structures. This is a structure number first, this is a structure number second, and this will be the structure number 3. If you look at as a structure number 3 carefully, what do you see over there? This carbocation is a tertiary carbocation, right? Tertiary carbocation, and that tertiary carbocation is a more stable. It is a more stable. Why it is a more stable? Because this tertiary carbocation is well stabilized due to the plus I inductive effect, plus I effect as well as hyperconjugative effect, plus I effect and the hyperconjugative effect. And as we know that inductive effect means what? Polarization induced in adjacent bond. Due to the polarization in one bond is called as the inductive effect, and hyperconjugative effect, it is a modification of the resonance effect. Whatever rules and conditions, they are remain same because it is just as a modification of the resonance effect, but that resonance effect is operating via pi bond. But here the difference, key difference between the resonance effect and the hyperconjugative effect, the resonance effect is operate via pi bond, whereas the resonance effect is operate via sigma bond. That is the difference over there. Now this is there. Now let us see, this is a what we can call it as a, this is a ortho attack of electrophile. We are getting as a number of such resonating structure. Out of that 3, if you look at this structure carefully or observe this structure carefully, what do we see? We will see here there is a tertiary carbocation, and as we know that tertiary carbocation is the most stable one, and in this particular example this carbocation, tertiary carbocation, is well stabilized due to the plus I effect as well as hyperconjugative effect. Hyperconjugative effect, that is the alpha hydrogen, depend upon the alpha hydrogen atom, number of alpha hydrogen atom present over there, number of hyperconjugative effect. There are 3 alpha hydrogen atom, and therefore you can draw the 3 hyperconjugative structure. In general, the hyperconjugative structure goes on increasing, the stability of that molecule goes on increasing. That is the general rule. And now let us look at as another one, another case. Here we are going to take the same starting compound, which is a toluene, right? And as we know that toluene is an electron donating group. It is an electron donating group, means it releasing the electron to the benzene ring. Now here the electrophile is attacking at a meta position. Now here the meta position, which is meta position, this is a meta position. Now this double bond is attacking to that electrophile, and after attacking to that electrophile, what do you get? See over here. Now this double bond, they are as it is, methyl group also as it is. Now here when these electrophile form as a bond over here, one of the hydrogen atom we can show here, and now when this double bond shifted from here and forming as a bond with that electrophile, what kind of the charge present on this corner point? And this corner point means there is a positive charge, means the carbocation is there, and that carbocation we can draw the resonating structure of that carbocation. Now look at here, double bond is here, and this double bond now shifted from here to here. Now when this double bond is shifted, what do you get over here? This double bond as it is, this hydrogen atom it is also as it is, electrophile as it is. When this double bond shifted from here, the positive charge get neutralized, and then CH3 group as it is, the positive charge which is comes on this carbon atom, and now we can show another resonating structure. Now this double bond is going to shift from here to here. We are going to get the next structure. Double bond will form here. This double bond, it is already there. This is the methyl group, it is already there. And now the positive charge comes on this corner point, this hydrogen atom, and electrophile we can show as it is. Understood this one? Now you can number this structure. This is the third structure. You can give number 4. This will be the 5. This will be the 6. When the electrophile attack at meta position, the positive charge is resonance is there, but it does not get stabilized because no such kind of the plus I effect or hyperconjugative effect you cannot see in this structure. If you look at if you observe this structure 4, 5 and 6 carefully, you won't see any such type of the stabilization effect by this when that attack at meta position. Now look at as another possibility when this group attack at para position. What do you get here? Electrophile attacking over there. This is ortho attack. Ortho attack we can call it as a, here will be the meta attack, here will be the para attack, right? This is a para attack. Now this electrophile is going to attack at para position. What are the structure you are going to get here? Now look at here, this CH3 group, it is as it is, this double bond and this double bond as it is. When this double bond start forming the bond with that electrophile, you are going to get here is a electrophile, here is a hydrogen atom. What do you think? What will be the charge? What is the charge on that corner point? There will be a positive charge on that corner point. Now again draw the resonating structure. Now this double bond shifted from here to here. What do you get? You are going to get the product over you are going to get the next structure. There will be a double bond. Look at here, this methyl group is an electron donating, positive charge comes on it, this double bond remains as it is. This is the electrophile and this is the hydrogen atom. Again we can draw the next structure over here. Another structure you may find over there. Now this double bond shifted from here to here and you are going to get another resonating structure. Double bond form here. This double bond, it is already there. This electrophile and hydrogen atom you can show as it is. When this double bond shifted from here to here, on that corner point there will be a positive charge. If you look at the structure number, now you can give the number of this structure. We have given the number here 1, 2, 3, 4, 5, 6. Now continue the number. This will be the 7, this will be the 8 and this will be the 9 structure. 9 hyperconjugative structure we have drawn over here. If you observe this structure carefully, you will notice that at structure number 8, carbocation, it is a tertiary carbocation, and this tertiary carbocation again well stabilized due to the plus I effect. Plus I effect exerted here in this particular case due to the methyl group. Plus I effect as well as there is a hyperconjugative effect, because this is alpha hydrogen atom, so there are 3 alpha hydrogen atom, and you can draw the 3 hyperconjugative structure over here. Hyperconjugative structure, hyperconjugation effect is there, and therefore, and as we know that number of hyperconjugative structure goes on increasing, the stability of this compound goes on increasing. So this is the what we can call it as the effect of electron donating group. If electron donating groups are there, if electron donating group present on the aromatic ring, they activate all the position of the ring. All the position, as we know that there are the 3 positions are there. Number 1 ortho, second one is a meta, and third one is a para. All these 3 positions get activated. They are activated means the electrophile can attack, the possibility of attack of electrophile at ortho position, it can attack at meta position, it can attack at para position. All 3 positions are there, means the orientation ortho, meta and para. But when electron donating groups are present, the ortho and para position are more higher activate, a higher activity present at ortho and para position. If you look at if you observe the structure number 3 and structure number 8 carefully, structure number 3 and structure number 8, the carbocation which is a tertiary carbocation, and that tertiary carbocation is well stabilized due to the plus I inductive effect as well as hyperconjugative effect, and due to this reason, when the electron donating group present on a benzene ring, they are the ortho-para director. Ortho-para director means what? Incoming group. When electrophilic substitution reaction, commonly observed electrophilic substitution reactions are nitration, sulfonation, halogenation, Friedel-Crafts alkylation, Friedel-Crafts acylation and diazocoupling. The incoming group, they are at ortho and the para position. So that is the conclusion we can draw from this overall discussion over here. Electron donating groups are present, they are the ortho-para directing. Why they are the ortho-para directing? Because when the electron releasing group gives the electron to the benzene ring, all these 3 positions are get activated, but as compared to the meta position, the ortho and para position are more activated, and that's why when we carry out the reaction such as nitration, sulfonation, halogenation, Friedel-Crafts alkylation, Friedel-Crafts acylation, the attack of electrophile preferred or favored at ortho and para position. And now when you are getting ortho and para position, among that also 2 are again there is a competition between ortho and the para product. In general, para product is a major as compared to the ortho, that is depending upon the substitution of the benzene and the incoming group. As the size of the incoming group, as the size of the substituent, it depends upon the the percentage of ortho product and the para product again depends upon the size of the substituent present on the benzene ring and the size of the incoming group. So that will decide the predominant, or what we can call as a prominent product. If the size of that substituent group, like as a alkyl group, it exerts as a plus I inductive effect, and therefore in such cases ortho product is a major as compared to as a para products. And suppose as a group like as a, what we can call it as a group like as a bulky group like as a NH C double bond O CS3 acetylene group, it is there. It is also as a ortho para directing, but the nature, the size of that substituent is a bulky, and therefore if you carry out the nitration, the major product obtained is a para due to the basically the steric hindrance. Steric hindrance is another factor coming to picture to decide the percentage of formation, whether the ortho product or the para product. As the size of the substituent goes on increasing, the percentage of formation of the para product is goes on increasing, because at ortho position there is a lot of steric hindrance, and when the steric hindrance is there, that increases the internal energy. And as we know that in general, as the internal energy goes on increasing, the stability of that molecule goes on decreasing. So in this way we can see the what we can call it as a, we can see how it is how it can be formed. So here just remember, if electron donating groups are present over there, they are the ortho para director, means they are activating the position at ortho as well as para position, and therefore predominantly we are getting as a ortho and the para product. And among these ortho and para, which one is a major and which one is a minor, that is again depending upon the size of the substituent, that electron donating substituent present on benzene ring, and the incoming group, whatever the electrophiles are going to attack. If the size goes on increasing, the percentage of formation of the para product is always predominant over that. So in this way, I think we have seen here the little bit theory regarding this one. In the next lecture, we are going to see if the electron withdrawing group is present, what type of the director they are. So that type of the thing we will see in the next lecture. I think with this, let us wrap up the today's lecture. Next time we will see another. Let us stop today here. Thank you. Have a nice day.